Good afternoon, everyone. My name is Siva Poornan. I am a doctoral student at the Civil Engineering Department of IIT Madras, and we are meeting here for the fourth week interactive session for the course of Matrix Method of Structure Analysis. So here we'll be discussing on the concepts related to what we have been hearing through the course of Matrix Method of Structure Analysis, and also we'll try to solve previous year assignment problems and discuss any questions we have. Right. Okay, so this is the fourth week. In the previous weeks, we had discussed about we had basically revised the concepts on basic structure analysis, and then we had discussed the previous year assignment problems for the week 1, 2, 3, and we'll be continuing from there in this session. So before we get started, I would like to know if you have any questions from what we had discussed earlier or from the course that you might be listening for the last 3-4 weeks. Are there any questions? Okay, then we'll get, if there are no questions, then we'll get started with the discussion here, right? So I just wanted to revise on the displacement based methods that we have been discussing last sessions, in the previous sessions, before we get started in detail with stiffness matrix and other matrix methods that we use for structural analysis. Right, okay, so we have been discussing about displacement based methods, right? Can somebody summarize what we have been essentially discussing on displacement based methods? So what is we have two different classes of methods, right? Force based methods and displacement based methods. In force based methods, we keep redundant forces as unknowns and then we solve for it, right, using compatibility equation. And in displacement based methods, what do? We find out kinematic indeterminacy, and then we solve for the the degrees of unknown kinematic quantities through equilibrium equations, right? And that's what we have been working on. And one such very systematic way of doing it is it's the matrix based methods, which we are learning now. Okay, so can you give an example where we have 1 degree of freedom displacement based method, like 1 degree of freedom problem? So we have solved many such problems. So I'll just, what is it? Propped cantilever. Yes, a propped cantilever is a good example of 1 degree of freedom system. So let's say we have a propped cantilever. Ignoring actual deformations, we can say that the only degree of freedom that is possible is the rotation at the end. So we know how to solve it, right? We can use even force methods to solve it, or if you want to use displacement methods, we first need to know what is the stiffness of the system. So we analyze the stiffness of the system, and then we find out for a given moment what is the rotation in it. So from our force method calculation itself, we know what is the stiffness of the system. So the moment versus theta relation, right? So theta relation, we know it is to be 4 by L, right? So m is equal to 4 by L times theta. Okay, so can you give an example of 2 degree of freedom system? So this we can probably continue the same beam with one more continuous span. Then we'll have a 2 degree of freedom system, right? So this is probably an example, good example of 2 degree of freedom system, where we can have two moments, and then we can find out what is the rotations at these points, m1 and m2. If I have, I can find out what are the rotations that are taking place at both these ends, right? The probable deflected shape for this could be something like this. So this would want to rotate downward. Okay, something like this. So we have a rotation theta 1 at this end and theta 2 at this end. And for this case, we saw that this m1 and m2 cannot be just a function of theta 1 and theta 2, but should be a function of both of these quantities. Therefore, we will have some k11 into theta 1 plus k22 into theta 2. Because if I apply only one of these moments, I expect that both theta 1 and theta 2 would appear, right? So similarly, m2 also would be related to both theta 1 and theta 2. So that is why we don't know these numbers, but we know that there will be 4 numbers, because we expect a linear relation. I'm sorry, I made a mistake here. It should be 1 2 and 2 2 here, right? So again I made a mistake here. It should be theta 1 here and this is theta 2. So we can write this as a matrix format, and we know that m1 m2 should be sum matrix times theta 1 and theta 2, right? That matrix will contain these 4 numbers. Okay, so I'm not filling this, but I assume that you know what numbers would come here, right? There'll be 4 numbers, these 4 quantities. Fine. So this gives a basic of how to do. We can extend this method to any degrees of freedom. We just saw for 1 degree of freedom system and 2 degree of freedom system. We can extend it to any degree of freedom system. And what we notice here is that in all these systems, one thing is common. We are relating the forces at the degree of freedom points, right, to the displacements at the degree of freedom points. The displacements or the rotations, right? Kinematic quantities at the degree of freedom points through a matrix, what we call as a stiffness matrix. So this is what the basic of using matrix method to solve any structure analysis problem. Okay, so let's get into more details and we'll see what is the concept of stiffness matrix. So from what we have discussed now, you should be able to say what the concept of stiffness matrix is. Can someone say what do you understand from understand by stiffness matrix from whatever we have discussed till now? What is the concept of stiffness matrix? What does a stiffness matrix does? It relates the force and the displacement. Yes, relates the displacements to the forces. Why not the other way? Because once we know the displacements, then we can find out the forces. That's how the matrix is formed, right? If you see here, if we know the displacements at these points, okay, if theta 1 and theta 2 are known, then we can multiply with these numbers to get this thing, right? If we do the other way, then it's called as a flexibility matrix. If we invert it and make it come here, then for a given moment we can find out, we can multiply with the flexibility matrix to find out the displacements. Okay, so the way stiffness matrix relates is it relates the displacements to the forces, right? So this relation can be read like forces are related to the displacements through the stiffness matrix. Okay, fine. And this is what will be the size of, so we'll go to the properties of stiffness matrix. What will be the size of stiffness matrix first? I have many questions, so just try to answer as much as you can. What is the size of stiffness matrix is the first question. Second is, yeah, mm, it's a square matrix. Okay, so that will come, that is one property. Let me first list all the questions and then probably you can answer what you uh, and is it symmetric is a question. Size is another question. And then what else can we ask? What will be the determinant of stiffness matrix? Okay, and another question could also be is it always a square matrix, right? Yes, so let's start from the first question. What is the size of the stiffness matrix? Yes, so it depends on degrees of freedom. So if degree of freedom, let's say it is a n degree of freedom system, right? And that then n into n is a size. Okay, so that's the right answer. So, but why is it so? N into n, where n is the degree of freedom, right? Okay. Why is it so? Why is it so? The answer comes from the basic definition of what a stiffness matrix is, right? So one easy thing to say is that we know that degree of freedom is n, right? If degree of freedom is n, since stiffness matrix is going to relate the degrees of freedom or the displacements at the degrees of freedom to the forces at the degrees of freedom, right? Therefore, if you have a matrix that has to be multiplied to the displacements at degrees of freedom, then it has to be of same, it has to have the same columns, right? So if you have m cross n, then if you have n cross 1, then you can have m cross 1 here, right? But so this gives an idea of why this should be n, because it has to multiply with this n, right? That's how matrix multiplication is possible. The second question comes that also relates to the last question of why it is a square matrix. Why this m should also be n? Why m should be equal to n? This should be n from the understanding that it should be able to be multiplied with the displacement of the degrees of freedom, which is nothing but equal to the degrees of freedom itself, right? At every degree of freedom, we can have a displacement. Therefore, this is n, where n is a degree of freedom. So this should also be n. But why should this m be equal to n? Probably the square thing should have been the second question. Then only we can talk about symmetry, right? So we'll talk about squares. So should it always be square matrix? Typically yes, right? Because yeah, you were saying something. Because we also need to have the forces. We also have the forces at every degree of freedom. It is possible to also have a force at that a force application at that point, right? So for example, if you have a truss system, so at every degree of freedom you it is possible to have two degrees of two displacements, u1 and u2, and you can also have f1 and f2, right? So the size of the force matrix also becomes n. So since this should also be n, therefore the stiffness matrix is a square matrix of size n by n, right? Because it relates n forces to n displacements. Therefore, it has to be of size n by n, right? Okay. So then coming to the question of should it be always symmetric? What do we mean by symmetric? Symmetric means we basically mean that if I have a stiffness matrix, if I take transpose of it, should it be equal to the matrix itself? Yes. Okay. But why? Yes, Maxwell's rule is one very good example. Can you explain it in detail? Force at 1 2 should be equal to force at 2 1 is not what Maxwell's rule is, right? Yes. Yeah. Yes. So basically, you're saying, yeah, yeah, you're saying that force applied at one for point I, which creates a displacement at j. Let's say it's dij. Then that should be same as the force that is applied at j and the displacement that is happening at I. Is it fine? Is it this is what Maxwell's rule is, right? Betty's law also is. So that is one way to prove it. You can actually find out that it happens. How do you prove it? How do you show that that rule makes the stiffness matrix to be symmetric? Or another easy way to explain symmetry of matrix stiffness matrix is to just say that what is the energy stored in the system. So let's say you have a complicated system, or even let's take a simple system first. So let's take a 2 by 2 system to understand how this happens. The previous example that we took itself will take. It's a continuous span with one end fixed. Right? It's a 2 by 2 system, right? You can have a moment and theta 1. Now what will be the size of stiffness matrix? It will be of the size 2 by 2. Now I want to find out the total energy in the stored in the system due to the application of these two moments. How do I find out? So I know that m1 m2 are related to theta 1 and theta 2, okay, through 2 by 2 as stiffness matrix, right? So what is the total energy stored in the system? Yes. So so if you would have gone through beam theory, you know that you can find the summation of total energy by finding out half into force into displacement or moment into theta, right? You can find out this. So basically, what is theta? We know that, or what is m? M is nothing but k into theta, right? So let us write this in matrix format. So I'm writing this m, okay, as capital M, where capital M means the total vector of moments, okay, and into theta. And theta again means a vector of things, okay, but it should not be m into theta because they are not compatible. It should be either m transpose theta or m theta transpose, okay. Then only you will have energy to be a scalar because this is of the order of n by 1, and this is also of the order of n by 1. Here it is 2 by 1, so you can take transpose and then multiply. This is what energy is, okay. Now what is m itself? We know it to be k times theta, right? So if you substitute it here, you will get u to be half into m transposes theta transpose k transpose into theta, right? What I have done is I have taken transpose. If I take transpose, I hope you know this. If I take transpose of this, then you should take the whole transpose, then the multiplication gets reversed. Okay, it's theta transpose k transpose. So this is what the energy is. But if I find out transpose of energy, what happens? If I take transpose of the whole thing, then this comes first, which is theta transpose, and then k comes, and then you have theta, right? Half remains there. But if I compare these two, I can see that k transpose and k should be same because u transpose is same as u. Why? If I take transpose of u, or if it just keep u, both of the things should remain the same. Why is it so? Yeah, exactly. Energy is a scalar, therefore if I take transpose or not, it should not matter. Therefore these two terms should be the same. By comparison, I can see that everything is same except for k. So we can see that k transpose should be same as k, right? So from energy sense also we can say. In fact, if you go to Betty's theorem, Maxwell's theorem, there also will be showing that that happens to be true because stiffness matrix is symmetric. Okay, so in fact that happens to be true because of this, and so we can show either way. You take any one thing and then show the other thing. Fine. Okay, so this explains why stiffness matrix is symmetric, right? So k transpose is equal to k is known, psi is also known. Determinant of a stiffness matrix. So what is the determinant of the stiffness matrix? What is it? I couldn't hear. 0 is right answer for given a condition, right? When does it happen? Before applying the unconstrained. Yes. So. Before applying the boundary condition. Yes. So before applying boundary condition, stiffness matrix turns out to be a singular matrix. A singular matrix in the sense its determinant becomes 0. And why does it happen? What is the reason? So structure is unstable. Okay, structure is unstable, so stiffness matrix becomes singular. Why structure becoming unstable should make the stiffness matrix to be singular? What is the reason? Because basically, what is a stiffness matrix? Stiffness matrix is what is it? It's a geometrical problem. It is geometrical. Material problem. Both. So stiffness is a material as well as geometric property. Okay, because you can just see from a 1 degree of freedom system, you have EA by L, right? So it will contain both geometry as well as stiffness relation. These one thing is a material property, one thing is a geometric property. Okay, in stiffness matrix you would have studied about this assembling and all, which we'll talk about quite soon. So you would have known that it will also depend on theta, right? So it depends on the inclination, the global stiffness matrix. right? And also it depends on the material that it is made, and also it depends both on geometry and material, fine. But the question is not about what stiffness matrix is. Yeah, the question is what stiffness matrix is, but the answer is not what I'm not expecting this, because in this context what do we need to know is why unstable structure means that the stiffness matrix is singular. That's the question. So first we need to know what the stiffness matrix does in this context, right? So basically stiffness matrix is relating the displacements to the forces, right? Or moments, otherwise rotations to the moments through a matrix, right? Now if what this matrix becoming singular actually means, this actually means that I would not be able to find out the moments for a given rotations. That's what it means, right? So basically, if what it means is for a given displacement, I may not be able to find out the forces. Or in other words, if it is singular, I will not be able to invert it. Therefore, I will not be able to find out the rotations for a given moment. So I can take inverse of this. Okay, if inverse is possible. Let's say this is k. So I can write k inverse times m, right? So if I am not able to find out k inverse, which would happen if I am not able to find out determinant of k itself. So if it is a singular matrix, then I cannot find k inverse. That means that I cannot find the rotations or displacements for applied forces. I think this is easier to understand. So what this necessarily means that I have a system, a complicated system, where I'm applying some forces. Okay, so let's say we have a complex system, and then we are applying different forces onto it. But with these forces, I'm not able to find out the displacements. The displacements we cannot quantify it. So what does it mean? It means that the structure is unstable, right? That's the definition of instability. For example, if you would have seen an unstable structure, let's say even if we take a square frame, a truss which is not triangulated, right? So let's say we have a truss system and we are missing the diagonal bar. So if I give a horizontal force, can you find out the displacement? Can you quantify the displacement and say this is the displacement? It's not possible. It can have different displacements. At all the displacements, it will not be in equilibrium, right? So the displacements cannot be quantified here, right? And that's why we say that it is an unstable structure. And that's the same thing that the same notion we're getting here. For a given forces, we are not able to find out the displacement, which means that it is singular, and which should happen not only for lack of boundary conditions, but also can happen for internally unstable structures. Okay, so answering the question, coming back to the question is determinant of a stiffness matrix happens to be 0 when we have an unstable structure, which could happen either with a lack of boundary condition or we have in internally unstable structure itself. Right? In that condition, even with the applied with boundary conditions, the determinant will still turn out to be 0, because the determinant turning out to be 0 is related to stability and not necessarily to just boundary conditions. Is that fine? Yeah. So when we have sufficiently stable system, what happens to determinant? What's the value of the determinant? It will be a finite positive value. Yes. And why should it be greater than 0? So you have a notion of positive definite, right? So you have U transpose KU to be greater than 0 because it's an energy term, right? Strain energy term. So that's the same reason why we say that K is positive definite. Okay. Anyway, it's not related to the course right now. Fine. Okay. So these are the properties of stiffness matrix. Any other properties that you have thought about or you want to ask? I think that is all. One question. Yes.
Maybe it's a stupid question, but I would answer it. When we assemble a global stiffness matrix, right? Before imposing boundary condition, we say that its determinant is zero. Okay.
Yes.
But now we are saying that after imposing boundary condition, it comes out to be non-zero.
Yes.
Right. Now my question is that even after imposing the boundary condition, you impose it in either the U matrix, U vector or the P vector.
Yes.
Right. Now the stiffness matrix physically remains unchanged. And only after taking a reduced form of stiffness matrix, we are able to solve it.
Yes.
Right. So how can we say that the global stiffness matrix after imposing boundary condition becomes invertible?
Yes. So there are two things that I want to point out. But by the way, this is a very good question, and it's no question is stupid, right? So it's a very good question actually. And one thing that I want to point out is boundary conditions. We always put it on displacements. Okay, forces. We, as far as I know,
Yeah, displacement, but
yeah,
we
yeah.
fill up with known forces.
Yes,
Sorry.
yes, right. So because boundary condition itself means that we are having some conditions on the boundary in terms of displacement. Okay, if
Yes,
we have
yes.
forces, then probably we will allow displacement at that point that is not coming in boundary condition. Anyway, so that is one point, and another point is, as you asked, we are imposing the displacements on the displacement vector. Yes. So you are right. It won't affect the stiffness matrix unless we reduce it considering the boundary condition. Okay. When we say the determinant of the stiffness matrix after applying boundary condition, we are actually meaning the reduced matrix,
Okay.
not the initial matrix that we had of the full size. Okay, that will, as you said, it will remain unaffected even after having boundary changing the u vector. We have to change the whole entire. We have to reduce it, and then we are solving the system, and that is what the system we are interested in solving. That is the system that we will be solving for f equal to ku. Okay. Before that, we will not be solving this relation. Here it will be reduced forces, reduced Ka and reduced U. Okay, so that is what we are saying, that this Kr will be having non-zero determinant. It will be non-singular. Okay, I hope that answered your question.
Yes.
Okay, any other questions?
So how to rearrange the reduced matrix?
Yes.
Then it becomes our
Yeah. So basically,
displacements are not continuous, or for unknown forces not continuous. How
not
to
con.
rearrange? Like if displacement vector is say u1, then 0, then u3.
Okay,
How to
okay, okay. Yeah, that is.
take it?
Yeah, we'll discuss. Actually, I haven't come to that point. I thought we'll solve a trust problem and then we'll actually see how to arrange. Right? Yeah, we'll get into the details of that now. Any other question from what we have discussed till now? No, right? Okay, then we'll go on to this topic of how do you find out the element stiffness matrix and then arrange it to form the global stiffness matrix, and how do we do that procedure actually, right? So let's take an example of a truss problem, or in case of axial members, right? So let's say we have an axial member, and usually we would have studied these axial members. We have been studying this from our high school. If you remember, a spring is an example of an axial member, right? So we take it as an axial member and we study this relation f equal to ku. F equal
Yes.
to, yeah, we would have studied k delta or ku. And this is a 1 degree of freedom system because the only point it can move is at, at, at this free end, right? Now the same thing is what we are going to study in trusses also. There is no difference. The only difference is going to come in that, in the case that we don't know, the boundary condition is not going to be so simple. The boundary condition at this point can also be free, because when you see an actual truss, all the points can displace, right? And that is why we have a free problem to be here, free displacements at both the ends, right? So we can slightly complicate it from this spring to a another spring where both the ends are not fixed. Okay, we can have a displacement at this end, let us call it as u1 dash, and we can have a displacement at this end also, u2 dash. we know this relation. We know stiffness is equal to F equal to K delta. And if it was an actual bar, we also know what that K is. Let's say we take a bar and we apply a force F. So F equal to, we know the relation, right? EA by L times this delta. Right. Okay, so this is the stiffness value is what we know already. Now let's say that both these displacements are possible. How would it be possible? Let's say we have a slotted system like a wall here, okay, and let's say we have another wall here, so that, and we are applying two forces. One force is like this, F1, and we are applying another force F2 here, okay, at this end, and both the points that can be displacement, right? U1 dash and U2 dash. Okay, so let's just denote it as F1 dash and F2 dash just to be consistent. Okay, now can you say how these forces are related to these displacements? Here we were able to easily relate it. F equal to A by L times delta, right? Where only one displacement is possible. Now if you have both the displacements possible at the two ends of the bar, then how do we relate these two forces to these two displacements? Can someone help me in doing that?
It will be like one consider fixed end at one.
Yes, that is the way in which we study structure analysis right now, but that is not a very intuitive way, right? So that seems to be very confusing.
Go for relative.
So is there a very basic way of doing it? Hmm? Yeah, you're right. You can fix one end and then do it, and that's the stiffness. That's the way we are studying it right now, and it's a very systematic way. But what is an intuitive way of doing it? So if you were in the undergraduates, how would you do it? What is it? I'm not able to hear it. So one way that I can think is I can just say that force, let's say F, the force at this end that I'm going to pull depends upon, so this force is what the total axial force that is coming onto the structure, right? So if I know what is the total elongation in the system, then I can find out, relate the forces to that elongation, right? Basically here delta is nothing but elongation. So I know stiffness is EA by L and the elongation should be delta, but here delta is going to be just U2 dash minus U1 dash, right? That is how it's going to be. So I can just say it is EA by L will still remain the same, and I can find out what is the force that is required to pull it. That is all, right? So I need to apply a force that is equal to the EA by L times elongation. Elongation is going to be U2 dash minus U1 dash. Therefore, I have related F2 and U2 and U1. But then how do I find out what F1 is then? I know that F1 dash should be just equal and opposite to F2 because then only equilibrium will exist in the structure, right? So F2 dash should be equal to, F1 dash should be equal to minus F2 dash. That is all. What is minus F2 dash? I can copy from the previous thing and I can say EA by L times U1 dash minus U2 dash. That's it. So therefore I related both the forces to both the displacements. So I can write it in a matrix format, in a neat format, F1 F2 dash, and I can put a matrix and I can fill this, right? 2 U1 dash and U2 dash. If I do that, what do I get at the matrices? Yes, but we have to take EA by L common outside first. Yes, so if I take EA by L common outside for F1 dash, I will get 1 minus 1 and 1. Fine. So this is the stiffness matrix for this stress problem when the displacements are allowed only along the direction of the truss, right? But in reality, the cases are not so simple. We went from 1 degree of freedom to 2 degrees of freedom. But in real situation, we can have the bar to be inclined in any direction. It may not be inclined along the displacements may not happen only along the direction of the truss. It can also happen at any point, right? So in reality, what can happen is you can have a truss oriented at an angle, and now the displacements can happen anywhere. You can take this nodal point to like this and then like this, right? You can take it here from here to here. So basically there can be u1 displacement degree of freedom, u2 degree of freedom, and then you can also have u3 and u4. So this is movement in a 2D plane. So now the how do we relate the stiffness, how do we relate the forces? Similarly, we can have forces on all these points, right? Correspondingly, we will have u1 f1 and u2 f2 and so on. So how do we relate them? How do we relate forces to displacements? So this is where the concept of transformation comes in, right? So basically we need to find out how these displacements are actually giving out the elongation, right? That's what we did in the last time also. We just found out how these displacement quantities are related to elongation. Once we know the elongation, we know how it is related to the forces through the stiffness value, right? And we can do the same. Basically what we need to do is that we need to find out what is the total displacement that's going to happen here, and similarly what is the total displacement that's going to happen here, and that will give a sense of elongation in the truss, right? And how do we relate it? So let's say that in the same bar we'll name this as u1 dash and this is u2 dash. How do we relate the displacements u1, u2, u3, u4 to u1 dash and u2 dash? What is it? I didn't hear you.
Solve forces V1 U2 along at U1 dash.
Yes. So how do we solve for them? How do we connect these u1, u2, u3, u4 to u1 dash and u2 dash? What do we use? We use compatibility. Basically these are kinematic quantities, so we need to use compatibility. So one thing that you can, there are many methods you can do it. One easier way to find it is basically u1 dash is what? U1 dash cost, if you take a cost component of it, you will get u1, right? So similarly you can find out u1 dash sin theta to be u2. Basically what we are saying is that how, if you are displacing this point to one, some u1 point, u1 dash point, how much distance should you go in along the horizontal axis and along the vertical to reach the same points, right? That's what it means. So basically if this is going to be u1 dash, then this is going to be u1 and this is going to be u2. That is all. Okay. So it's just cost component and sine component. You could do the other way also. Basically here what we are doing is we are relating, we are finding out, this is called the global coordinates. You would have known by now, right? So global means in the global structure we are seeing how it is looking. So there are many members, and in the global sense this is x coordinate and y coordinate we are having, and that's why we took this as u1 and u2. Not we are not seeing how the member is inclined, we are only seeing it and we are converting into that, right? And these are called as local coordinates because these coordinates are inclined along the direction of the local member itself, right? So these are local coordinates and these are global coordinates. So here what I'm doing is I'm converting local coordinates to global coordinates. Okay, you could do the other way also. In the course lecture you would have seen it in the other way. Anyway you could do it. This seemed to be more intuitive to me, that's why I'm doing this way. Okay, so u1 dash sin theta is equal to u2. Similarly you can also do the other way around, right? u2 dash cos theta is equal to u3 and u2 dash sin theta to be u4. Is this clear? Is there any mistake in what I have done, or is it okay, fine? Okay, then how do you write this in matrix format? You could just write it as u1 dash u2 dash. So you could create a matrix from this, right? You can just write u1 u2 u3 u4 to be related to something into, I have u1 dash and u2 dash. Can you fill that something? So what it would be, u1 is equal to, so let's just write cos theta to be yeah, just cos theta to be c and sin theta to be s. Okay, just as a short form. Okay, you could also in the course you would have be writing it as lambda x and lambda y. Okay, we'll come to that later. As of now, we'll just write it as C and S. So what you have here, C, and then here 0, because it's not related to u2 dash at all, right? And again u2 is related to u2 is yes and 0, right? It's related to u1 dash only, yes. And u3 is going to be 0 and C, and u4 is going to be 0 and S. That is all. So basically you are able to convert local coordinates to global coordinates by multiplying with this matrix, right? So basically we define transformation matrix to be that matrix which converts the other way. It converts from global to local. That's what is the definition. You could define it any way. Somehow the books are defining it this way. But in your terms, if you are defining the other way, that's fine. Definition do not matter that much. So I'm just keeping the consistency and defining transformation matrix to be that matrix which is able to convert from global to local. Okay, G to L. If you do that, then what is happening here? It is not transformation matrix, it is other way around. It is able to convert from local to global. Okay, so if you actually see the other way, it happens to be a transformation of transpose. Okay, this happens to be transpose of the earlier matrix. You would have seen in the course, I hope. So we are able to convert global coordinates as t transpose of local coordinates. Okay, this is how we are writing it as. Local coordinates are going to be u1 dash and u2 dash, and this is going to be u1 2 3 4. We have what we have done is we have done nothing related to stiffness. We are just converting one sort of displacements to another sort of displacements, like what we did here. In this case, what did we do? This is just directly subtraction, right? We knew it because we know that u2 dash minus u1 dash is going to give the total u. Here it is not so straightforward. What we have done is we have taken component of it to convert from one coordinates to other coordinates. Once we do this, now it is very simple, right? Because we know once u1 dash and u2 dash are known. So how do you find out u1 dash and u2 dash? You just need to, it so happens that t transpose happens to be identity. Okay, transformation matrix is also an orthogonal matrix. Okay, so basically what we can do is that we can multiply t transpose on both the sides. So what I'm saying here is I'll just go to the next page and do it. Just remember this equation. Okay, so what we are saying is we have global coordinates to be equal to t transpose times local coordinates. Okay, if I multiply t on both the sides, then t transpose happens to be unity. You can just check it out. How? Because what is t transpose? T transpose is, by definition, it's c0 s0 0c and 0s, right? And what is t? T is just the transpose of this, so you will get c0. Yes, I'm sorry, you're right. C0 yes, if I multiply both these things, what do I get? C into c, like that. If you do, you will observe that it's c square plus s square, right? And 0 0 c square plus s square, this is what you will see. So basically it will become unity matrix 1001, right? Identity matrix, right? So that is how t transpose becomes identity. Therefore ul becomes local coordinate is equal to t times ug. So if you want to convert global to local, you have to multiply t. If you want to convert local to global, then you have to do the other way. T transpose you have to multiply. That's what you understood this point. Basically I have written ul to be here and ug I have written it here. Okay, fine. So this is what we need, because we need to convert from global to local, because once these displacements are known, u1 u2 u3 u4, we are converting into local. Once we know local, we can find out the relation, right? We know how these are related to local. So we know f1 f2, these local forces f1 dash and f2 dash are related through, just now we found out in the previous slides, right? ea by l times 1 minus 1 and 1 times u1 dash and u2 dash, which are nothing but local coordinates, right? So once we find out local thing, we can substitute it here and find out f1 f2. So what can we do? We can just say this, I will denote it as force local. Okay, So force local is equal to EA by L times 1 minus 1 minus 1 1 times U local is nothing but T times UG, right? So basically I'm able to relate FL to UG, but actually what I should be doing, I should be relating FG to UG. So you can also convert forces from global to local, and it also follows the same procedure. Okay, so we could have also, instead of writing u1 dash is cos theta is equal to u1, we could also write f1 dash cos theta is equal to f1, right? So if you have forces here f1 dash and f1 to be here, from taking components we know that f1 dash cos theta is equal to f1. So that also follows the same law, right? So we know that f f fl is equal to t times ug, or fg is equal to t dash times fl. Okay, so t transpose. Okay, so using this relation, or you can write fl is equal to t times fg. You can use this relation, you can substitute it here. Okay, so if I substitute it here, what happens? Fl is equal to t times fg, therefore it will become t times fg is equal to ea by l into this thing, whole thing will remain same, right? I can just multiply t transpose on both the sides. So what will happen? T transpose also will come here. I can just take ea by l outside because it's a scalar. I'll have t transpose, this 1 minus 1 minus 1 one thing, and then t, and then ug, right? Now if you see here, what t transpose t is going to be identity, so I don't need it anymore. I just have fg. So I know that fg is going to be related to ug through this thing, and this thing is what we are calling it as stiffness matrix in the global coordinate. Is it fine? Are there any doubts in this? Okay, so basically we fg is going to be related to ug. Force and global coordinates are going to be related in to displacements in global coordinates through the stiffness matrix in global coordinates. Okay, and that will be of the size same as the what we have in the global coordinates as this thing. So we had 4 cross 1, if you remember. This also is 4 cross 1, so stiffness matrix will be of the order 4 cross 4. And what is this k actually going to be? This k is nothing but t times t transpose times, right? Yeah, t transpose times ea by l also will be there. ea by l t transpose times 1 minus 1 minus 1 1 times t. That is all. If you do this calculation, you will find out that it forms out to be a neat 4 by 4 matrix. Okay, so what is this t and t transpose are? We know that t is going to be cs 0 0 0 0 cs. That is all. So basically once we know this, we are able to find out the stiffness matrix in the global coordinate for any truss member inclined in any direction. So what is the cs? It is cos theta, which is going to be which depends on what is the inclination of the truss member. Okay, so it gives a sense of what this theta x is. Now we can just name this as theta x, and the other theta to be along the vertical direction to be theta y. Once we name that, instead of writing sin theta x, we can write it as cos theta y. So basically we can say cos theta x to be lambda x. It's a new terminology. The meaning is the same, and instead of writing it as sin theta x, I can write it as cos theta y. Right? I know they are complementary. Therefore, it can be written as lambda y. So you can also rename these things to be lambda x, lambda y. This is lambda x and lambda y. Okay. So once you have this matrix, you have the whole stiffness matrix for any truss member, right? Now comes the question of, if I have multiple members, then how do I find this total stiffness matrix for the entire structure, right? And that's where we talked about assembling the global stiffness matrix, right? So how do we do that? Let's say I have two members meeting at a point. This is one truss member and this is another truss member. Okay, so we have, this is first node, second node and third node, and let's go from here to here. Okay, so what do we mean by going is that basically we need to know where the theta is inclined towards, right? So if this is the direction of the member, then theta x is going to be this is the inclination of the member, then theta x would be this thing. Okay, so it will be negative depending upon the direction we take, right? Okay, so how do we then find out that we know the stiffness matrix for this thing from the usual procedure, whatever we had adopted now? We can also find out the stiffness matrix for this member using the same procedure. Then how do we assemble both of these two things? What do we use? We use a condition that the displacement degrees of freedom, we would be first actually finding out the stiffness matrix of these two things independently, right? So we will say this is u1, u2, u3, u4, right? And if you do for the second thing, you will have this is u3, u4, u5, u6. So let's say we have found out 4 by 4 stiffness matrix for these two members. This is member 1 and this is member 2. We have found out a 4 by 4 stiffness matrix for this first member. We have also found out the stiffness matrix for the second member. Then for the whole structure, what should be the size of the stiffness matrix? 6 by 6, because we have only 3 nodes, which means that essentially we have only 3 degrees of 3 into 2, 6 degrees of freedom. Therefore we will have a 6 by 6 stiffness matrix. How do we convert this 4 by 4 and another 4 by 4 to 6 by 6? So this will be pertaining to, if you would by the yes, so how do we, the definition of stiffness matrix is it relates the displacements to forces, right? So it is basically relating u1, u2, u3, u4 to f1, f2, f3, f4, right? Basically these rows and columns are pertaining to 1, 2, 3, 4 degrees of freedom. And why are the columns also like that? Because we know they are going to be related to f1, f2, f3, f4, which means that these columns are going to be pertaining to 1, 2, 3, 4 degrees of freedom. Okay, same thing, same argument can be said here, and then these are pertaining to 3, 4, 5, 6 degrees of freedom, and same thing applies to here, 3, 4, 5, 6. So basically we observe that commonly this 3 and 4 degrees of freedom, the stiffness of 3 and 4 degrees of freedom from both these members are existing in both these matrices, right? So can we just add them? Why can we add them? Why shouldn't we just take multiplication or do something else? Why should we necessarily add them? So let's say that we have a 2 by 2 value here pertaining to 3 and 4 degrees of freedom from both rows and columns. Similarly, we have a 2 by 2 submatrix coming from this 3 and this 4, right? So there are 4 values here and there are 4 values here. Can we just add these 4 values? Why is it possible to add? Because we have seen something. Yeah. Yes. No, displacements are not distributed. Displacements are the same. Forces are only distributed, right? Yes. So for point 2 or node 2, we know that the forces are going to be distributed to both these members and displacements are going to remain same. This means that both these members are in. Exactly. This is the same concept that we have discussed before also. So when we have these two, let's say we have a spring, like we have discussed this problem earlier, if you remember. So if I have let's say a fixed beam with a roller in between or hinge in between, and if I apply a moment here, then we have seen that the stiffness of this member is 4 by L. The stiffness of this member is also 4 by L. If both are identical in length and everything is same, then we know the stiffness of the whole member is just going to be 80 by L, right? And why are we able to do that? Because we know that, yes, we know that they are in parallel, right? And that's the same thing that's happening here. If you see both these points, they're having same displacements. The rotation is going to be the same, moment is going to distribute it, right? And that's what we saw, that if you have two springs in parallel, then if you apply a force F, it will go as F1 and F2, and you'll have the displacements to be same. Both will have a delta displacement, right? And the same thing is happening in this point. That is why we are able to add the stiffness of from the one system at the same point should be added to the stiffness of another member, because both the points are going to be in parallel when you attach them. Okay, so that is why when you assemble the global thing 1 2 3 4 5 6, so this 3, and here also you have 1 2 3 4 5 6, so you have 3 and 4 and 3 and 4. These 4 points should be addition of the values from these two submatrices. Okay, and other points you can similarly assemble 1 2 and 1 2, you can just, other points they are not having any added values. Okay, and once you do that, you will observe that you have got the stiffness matrix for the entire structure. Okay, but the stiffness matrix will be singular, like what we have discussed earlier, because for any given forces, can you find out the displacements? It's not possible, because what it means is basically I'll have 6 forces here, F1 F2 F3 till F6, right? And similarly I have U1 U2 U3 till U6 in coming here. Now the question is, for any given displacements can I find out forces, or for any given forces can I find displacements, is the question. It's not possible, right? Because if I, this system, what does this system mean? Basically I have a V link like this. I have two links with a truss point here. This is an unstable. If I give a force here, displacement could be anything. It can have infinite values of displacements, because it's just a free hanging system, right? Therefore, it means that the stiffness matrix and the flexibility matrix we cannot find, or in other words, stiffness matrix would have a zero determinant. So we have to arrest some of these things. We have to say that okay, I have a hinge here and a hinge here, then make it stable, then for any given forces we would be able to find out the displacements, or other way around, for any given displacement we will be able to find out the forces. Okay, so arresting this basically means that we are arresting u1 u2 and u5 and u6, right? So basically we'll have u1 u2 u5 u6 to be 0, only non-zero values to be u3 and u4 to be non-zero. Okay, so these things will become 0, and you have non-zero values only at these 2 points, right? And what about forces? What happens to forces? Yes, you have F3 and F4. Other points, why should the forces be 0? You need not. Basically, you can have forces, but in typical situations you would not have, because if you have a boundary condition, applying a force there doesn't make sense at all. If you are applying a force here, it will directly go to the boundary. It will directly go to the support condition. Okay, therefore if your displacements are 0, applying forces that do not make sense. Even if it is applied, you can just take them to be 0, because they would not contribute towards the stiffness of the system, but they would directly get into the support. Therefore you can assume to be 0, or even if they are non-zero, if you take them to be non-zero, it wouldn't matter, okay, when you solve the problem. So what you need to do is that you basically need to subtract out the rows and columns of all the degrees of freedom which are for which the displacements are 0. Eliminate those rows and columns and consider only those rows and columns for which the displacements are non-zero. What I mean by that is basically whatever I have striked out here, right? Red pen. So those are the only things where the displacements are not 0, 3 4, right? So if 3 4 are not 0, take only 3-4 rows and 3-4 columns and consider that stiffness, and you take only F3 and F4. So F3 F4 is going to be related to K reduced, which is going to be these 4 numbers, to U3 U4. That's all. You solve the problem. For F3 and F3 F4 will be known because those are going to be applied forces. Okay, so you don't know U3 U4, you just solve for them. But the question is, why are you able to do this? How are you just able to eliminate all the rows and all the columns which you have as 0, and you are able to take only the non-zero terms? That's the question, right? Is that the question that you had asked earlier? Okay. Can someone, Gaurav, probably, do you have any idea of why we are able to do that? Okay, no issues, no issues. Yeah, the question is, we had said that if we are having zero displacement terms in this in the displacement vector, then whichever values are not zero, pertaining to those rows and columns only, we will take the stiffness matrix. That means that we have only these 4 values, right? U3 and U4. And similarly, we take only F3 and F4, and stiffness matrix just becomes a 2 by 2 matrix with only 4 terms, right? And we are able to say that this is the reduced stiffness matrix, and we are relating the known forces to unknown displacement, and we are able to find out the unknown displacements, right? The question is, why are we able to reduce like this? How are we able to say that we can just cut off these, eliminate? Let's say I'm taking a new color, green color. We are eliminating all these elements, right? We are not considering them at all, right? How are we able to do that? We are only taking the red values, 4 values from here. Why is it possible to do that? What is the reason behind doing that? How are we saying that whenever there is a zero displacement at that point, eliminate the stiffness matrix pertaining to that row and that column? That's what we are saying, right? But how are we able to say that? What is the logic behind it? Hmm. 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 Yes. Yes. So basically, the question that somebody, I don't know, you or Meenakshi, who had asked. Yes. So if, yeah, what is the question? Yes. Okay, okay. So basically, it doesn't matter how the arrangement of degrees of freedom are there, which are becoming zero or non-zero. It doesn't matter. What matters is that we are able to always rearrange them in such a way that it can be rearranged so that they all come together. Because matrix is like that, right? So if you remember what actually we are doing by this matrix, we are writing F1, F2, F3. Okay, I'm just giving 3 numbers. Maybe 4 numbers would be able to illustrate it better. Let's say I'm having these 4 value F1, F2, F3, F4 for some system, and I'll have a 4 by 4 matrix, and I have U1, U2, U3, U4. Now it doesn't matter which of these becomes 0, because what does it mean when I'm able to write it like this, right? What does it mean? Basically, it means that F1 is equal to K11 into U1, K21 into U2, and so on, right? So it's a linear equation, right? Depends on U1, U2, U3, U4, right? Now, can I just interchange all these things? Can I just write F2 and F1 interchange? Similarly, can I interchange, yeah, U2, yeah, if I interchange these two numbers, can I interchange these two things? Yes or no? Why? If I interchange, what happens? In the first case, F2 will become the second, this value into U1, this value into U2, and so on, right? And if we interchange also, F2 will become the same thing, whatever comes up on the top, into U1, into U2, and so on, right? It will remain the same. I don't know if you're able to visualize it. Let's say this is what is the first case. You have F2 here in the second column, I mean in the second row, and then U1 is here, okay? Now let's say that after interchanging, f1, f2 has come here. Okay, this number would have also come here, right, on the top. Now also we are multiplying this number to u1, right, and the second number to u2, right? So basically the expanded equation will remain the same, is it not? So in that sense, you can interchange these rows and these rows and f1 and f2 such that you can make the known numbers to come on to come together. So how do we change? So how do we change this u1? We talked about changing these forces. So can you now imagine how do we change this u1 u2 such that the zeros are coming together and the non-zeros are coming together? What do you need to do? Here you are changing the rows. There what you need to do? Just analogous things. What is it? Columns, right? So if you, let's say that I want to interchange this u1 and u2. Okay, let's say in the first case I'm having u1 on the top and u2 on the bottom. Okay, so if I write the first equation, there's no interchanging here in the first things. Okay, now let's say first u1 u2 are there. Now I want to change u2 to come on top and u1 to come on bottom. What should I do? So how would the equation read? Initially it would be reading f1 equal to this thing, this into u1 plus this into u2 and so on, right? Now if you interchange, what will happen? Instead of multiplying, yes, so if I have to change this, I basically need to column, I have to interchange. I have to interchange this first thing, this will be second thing, because all the columns, if these numbers would be multiplying with the first term here, and all the blues will multiply with the u2 here. That's what would give this. Now if I want to change these things, I just need to interchange these columns also. Yes, so it is always possible to interchange them and accumulate all the zeros to one ends. Okay, the matrix properties are like that. Therefore once you change them, after that, so that is why people usually write that when you have f system is equal to, you have k unknowns, knowns and things like that, right? And you have, at last you have u knowns and u unknowns. So u knowns are going to be 0 or the other way around, however it is. You are able to split it like this because they are saying whatever stiffness matrix you get, just arrange the columns in such a way that you have uk to be on the top and u to be unknowns. And that stiffness matrix corresponding things, you can just cut it and say that it will have 4 quantities, and then those 4 quantities can be written as ku k. I'm sorry, this will be k k k, sorry. Okay, but I hope you are getting the idea. Okay, this will be k k k. You're able to do that because first you are always able to write this as uk, and uk are going to be zeros, you knowns. Okay, mostly, not necessarily always zero. You can have cases where they are finite and non-zero, but still you know them. That's what the idea is. You know these u values and you don't know these u values. Okay, and how many other rows are appearing here? Same number of rows and same number of columns. You cut it, and then you are able to split them into 4 different sub matrices for the stiffness matrix, and that you then say that you are able to just take only one sub matrix of that. That's what we saw here. So it doesn't matter where the sub matrix is appearing. In our case, it appeared to be at the center. Okay, it could also be appearing in one corner. That's what you would have usually seen in the course, right? Any other questions? Should I elaborate more on that? Okay, I hope there are no questions. That I haven't still discussed. What I have discussed till now is to say that it doesn't matter whether we have the zero uh, displacements to be occurring together, or if we are having them separated by the known displacement and the unknown displacements coming. Yes. 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 So that part I have not discussed yet, but we can also show that. So the first thing that what I have said till now is that we can always write the force and displacements can be splitted in this way. We know that displacements, however they occur, we can always group them to be knowns first and unknowns second. This is what we have discussed till now. This is always possible is the point that we have discussed till now. Yes. Yes. Yes, we'll come to that. Yeah, I understand your concern. Yeah, so the concern you're raising is that how do we easily solve the problem? We'll come to that. Conceptually, what I'm trying to say is that we can do this. Once we do this, then why it is necessary to show this is that then only we can prove that whenever we have a zero displacement, those rows and those columns we can just delete off and then take the reduced stiffness. We are going towards that. We have not reached that point yet. So once we are able to split them into known and unknowns, then we also say that whatever stiffness matrix arises from after that splitting, we are going to name it as k k k, or just 1 2. Okay, it is just difficult for me to remember what is k. Just one, yeah, 1 1. You're right. Sorry, k 1 1 k 1 2. This is a bigger. It's not just a number. Okay, it is a submatrix itself. K 1 2 k 2 1 and k 2 2. Okay, this is also I'm going to name it as f1 and f2. Okay, this is also I'm going to name it as u1 and u2. Okay, now what we are saying is that f1 we know it to be k11 times u1 plus k12 times u2. Now we know that u1 is going to be 0. Okay, why? Because we can always make u zeros to come on top. That is possible, therefore I'm able to write it like this. Therefore this is going to be 0. Okay, so that is why f1 is going to be k12 times u2. Right, and that is the forces that I'm going to be interested in. Am I right or not? Let's see. Anyway, this is one equation. Another equation that I have is that f2 is equal to k11 times u1, I'm sorry, k21 times u1 plus k22 times u2. Right, again I know that this is going to be 0. Okay, so basically here what it means is that f1 is, if it is going to be 0, those places uh, my forces are not known, right? So basically these will become the support forces if you think about it, because if you go to the truss and see whichever force places I'm applying the displacement boundary conditions, I don't know the forces that are coming there, right? If I take the free body of the structure, there will be a reaction f1 and f2, which I don't know. The only forces that I know are the places where displacements are not known. Okay, they usually come in complementarily. Okay, so basically what I'm saying is that I don't know f1, so this is also unknown. Unknown they'll mark in red. Okay, so f1 is unknown and u2 is unknown here. u1 is known to us. Okay, but f2 are known, so I'll mark knowns in green. Okay, so now what we can see, there are two unknowns here in this equation, so we cannot solve this equation directly. Okay, f1 is also not known, u2 is also not known. Okay, the second equation if you see, it's going to have only one unknown, right? u2 is the only unknown, so you can solve for f2 first. So if I rewrite this equation, we're going to have f2 is equal to k22 into u2. You can take inverse on, there are many ways to solve it. Okay, you can take inverse as the easiest way, and this equation basically says what? If you want to find out f2, okay, if you want to find out u2, you can just take that row and that column and use that matrix, right? And that's what we are doing, right? And this equation basically says that take only that submatrix which corresponds to u2, those 2 and 2, right? You are saying 2 and 2 here, which means that you take those rows and those columns and the submatrix which belongs to that, take that submatrix and use it for finding out u2 through f2. Is that clear? So this now answers the question of how we are able to just take one submatrix and solve for the unknown displacements through known forces, right? So this is the question that we had initially asked. The question was how we are able to just eliminate everything and then take only those uh, columns and rows pertaining to the unknown displacements and use those forces to find out the displacements. That was the original question, right? So now we are able to show it mathematically that that is true, that we can use only k to 2. It doesn't depend on k11, k12 and k21. Those values do not affect what f2, what u2 is going to be, right? Then why are they important? Once you find out u2, you would be able to substitute in this and be able to find out f1. For those values, k12 would be important, okay? And k12 is same as k12 and k21 will have a transpose property, okay? Fine. So this now it is also this k to 2. Basically, what it means is that it doesn't matter this k to 2 is in one corner or not. For example, I could also have the zero non-zero terms to be somewhere here and here. So just take, in that case, just take whatever rows are happening. If let's say first and last, then just take first and last row and first and last column. Those values only you take. Okay, so it doesn't matter whether they are coming together or not. That is what forms k2 k22. Okay, let's say in the case of where you are having this and this to be the only unknown displacements. Okay, so I think this answers all the questions that we had asked earlier. Are there any other questions? Understand which part of it? Okay. Yes. Yes. So how that is true is not clear. Okay. Yeah. So okay. Okay, so what we are basically saying is that if you have if you are if it is not related to forces or displacements at all, it's just a matrix problem. Let's say you have one vector being related to the other vector through a matrix. Okay, so just for the namesake, we will keep it as forces and displacements because we are familiar with that. So we, yeah, sure. You are going to give numbers. Is it going to be an assignment problem which I'm going to be this year assignment? Okay, I'll give an example because I don't, maybe you can give the example so that I can try to modify it and work on it. Yeah, yeah, you give the example. If you can probably share the screen if you have something on. Okay, okay. If it is a 8 by 8 problem, it's going to take more time to write it here, right? Okay, 4 by 4. You make it 4 by 4. Yeah. P1, P2. Okay. So these three are P1 and P2 are unknown, P3 and P4 are unknown. Okay. 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 So in this case, you have to solve for these unknowns and this unknowns, huh? Okay. So basically, what do you need to do? There are four unknowns, right? That you need to solve it for. So just expand the equation and solve it, right? So okay. Yeah. Okay. We'll just make it not continuous. Don't worry. So we'll make it u2, u3, and 0. Is that fine? This is fine? Yeah, so now what we need to basically do is that we need to, as we said earlier, we can just delete the rows and columns which are pertaining to zero displacements. Okay, so basically what I have to do is that I have to cut off these rows and take only these terms only pertaining to 2 and 3, which means that 2 and 3 here, 2 and 3 here. Okay, I'm going to take these. Maybe taking red is not your correct color, so I'll cut off these things. Okay, and I am going to take only these green values. Okay, so which gives that P2 is equal to, I have P2 is equal to, if I use the rest of the equation, I know P2 is equal to this value. Okay, into U2 plus this value into U3. Fine. And then the other equation that I have is minus 3 is equal to this value into U2 plus this value into U3. Okay, all these four numbers you can write it. Now you have actually two variables or three variables, therefore you will not be able to directly solve this system. But are you also having a case where two unknowns are coming in the same equation, P2? In your example, is it happening like that? You understand what I'm asking? This would not typically happen because, yeah, so in your case, you're either you in a row you either have, yeah, so the way we have taken this example is not right. So how we should have taken this is, I'll just modify this thing so that it becomes, okay. So what I will do is I'll just make it P1 uh, 0, P2 0, not 0, yeah, 0 only, right? Or some number, right? You have some number, minus 3, P2 4, right? So you have four values, and then you have this is to be 0, U2 and 0, U3. Is this fine? Usually why this is how we solve is that, as we said earlier, whenever you have a displacement to be 0, there you have an unknown support reaction. Okay, and wherever you don't know displacement, that's where you apply the forces. The forces would be either 0 or known. Okay, that is why it always happens that you either know the forces or the displacements. Okay, both the things not being known is can happen, but we don't start those in this, at least starting, we don't want to study that first. Okay. Okay, fine. So now you can just take the delete the rows and columns which are pertaining to the zero displacements, right? So I'm going to delete this first and third row, first and third row. Okay. So whatever is left is second row, these four numbers. Now I'll just write the total entire thing. What do I get? I know that minus 3 is equal to something into U2 plus something into U. Oh, sorry, this should be U4, right? U4. And you have 4 is equal to something into U2 plus something into U4. That's it. No, you have. So actually I don't need to even expand this. What I could do is that, what I could what I could just do is that I can just use the matrix. I can just write minus 3 4 is equal to that 4 by 4 values, right? This green value into U2 and U4. Just invert this matrix. That's it. U2 U4 is equal to, let's say this is KR. So this is KR inverse minus 3 and 4. That's it. Yeah, that is exactly what we are doing here also. Okay. Any other question? Okay. Then thank you for attending. We'll close the session here. Yeah, thank you.